Hello friends, I welcome you in lecture number 14 on recurrence relations. In this lecture, we are going to discuss about solution of recurrence relation using generating function. In previous lecture, we have discussed the meaning of generating function. We just recall that suppose we have some sequence an, then the generating function for this sequence an is defined as gx equal to sigma an times x raised to n equal to 0 to infinity. And we have seen how to write down the generating function corresponding to given sequence in previous lecture, and we have derived some generating functions for some standard sequences. And if you have not seen that lecture, I suggest you to watch that lecture first, because we will require all these things in upcoming lectures as well as in this lecture. So this is the summary of lecture number 13, in which we have seen that if our generating function is given, then we can decide the nth term of the corresponding sequence. So we will remember this. Suppose we have c over 1 minus x, then this is the generating function of the sequence an whose terms are constant, an equal to constant for all n equal to 0, 1, 2 and so on. So if I know that the sequence an corresponding to this generating function is known to me, then I can directly write down the formula for this generating function. Now I know that this generating function corresponds to this formula an equal to c. Therefore, I can write down the generating function directly. I can write that sigma n equal to 0 to infinity an x raised to n, and an for this generating function is c. So I can directly write down c into x raised to n. So c is arbitrary constant. If I have 2 here, I will write 2 here, 2 into x raised to n. Suppose I have 20, then I will write 20 over 1 minus x equal to sigma 20 raised to 20 into x raised to n. Similarly, if I have this generating function x divided by 1 minus x square, then the corresponding sequence is an equal to n. So I can represent this x over 1 minus x whole square as sigma an x raised to n. An is n corresponding to this generating function, that is n times x raised to n equal to 0 to infinity. Similarly, if I have c over 1 minus bx, then the corresponding sequence is given by an equal to c times b raised to n. Suppose I have 2 over 1 minus 3x, then here if I compare, then c equal to 2 and b equal to 3, and the corresponding series is n equal to 0 to infinity. An x raised to n, an is c times b raised to n here, and if we compare, c is 2 and b is 3, so 2 into 3 raised to n, c into b raised to n, c is 2 and b is 3, so I have written 2 into 3 raised to n into x raised to n. So if you can remember these formulas for generating function and corresponding sequences, then you can directly write down this type of terms in the solution. And if you cannot remember, then also it is fine. You can use binomial theorem or binomial series expansion to write down the sequence or nth term corresponding to the given generating function. So with this in mind, we are going to solve this recurrence relation using generating function in this lecture, and this question was asked in GTU Winter 2020 exam. Use generating function to solve a recurrence relation an equal to 3 times an minus 1 plus 2, and initial condition is a0 equal to 1. We can see that here I have n minus 1, and if I compare with the standard form of recurrence relation, that is an equal to c1 into an minus 1 plus c2 into an minus 2 and so on, ck into an minus k plus f of n. Then if we compare this recurrence relation with this standard form of linear recurrence relation, then we find that we have k equal to 1. Therefore this is a linear recurrence relation of first degree, or degree of this recurrence relation is 1, and we have f of n equal to 2. Therefore this recurrence relation is non-homogeneous. So first you have to decide the degree of given recurrence relation. Now first step is decide the degree of recurrence relation which is given by comparing it with the standard form of linear recurrence relation with constant coefficients. And after deciding the degree, you have to multiply your recurrence relation or the equation representing recurrence relation by x to the power n. So first step is determine the degree of recurrence relation and then multiply both sides of recurrence relation by x to the power n. So that I have done here. This is multiplied, each term is multiplied by x raised to n, and the corresponding recurrence relation is an x raised to n equal to 3 times an minus 1 x raised to n plus 2 times x raised to n. And here n starts from 1 because this is a recurrence relation of first degree. After multiplying by x raised to n, we have to take sigma or summation on both sides for all possible values of n. So I will apply sigma on both sides. So sigma of this plus sigma of this, and here n is taking the values from 1 to infinity because we have recurrence relation of first degree. Here n is greater than or equal to 1. Suppose we had a recurrence relation of second degree, then our n was n greater than or equal to 2. So whatever range of n is there, or whatever the degree of recurrence relation is there, your summation index will start from that degree. So here our summation is from n equal to degree of recurrence relation to infinity. So in the next step, we will take sigma n equal to 1 to infinity, or we will take summation on both sides, or we will sum all the values corresponding to values of n. Here values of n are infinite, so we are taking sigma n equal to 1 to infinity. So this is going to be sigma an x raised to n, and in this second summation, here we have 3 independent of n, so we can take it outside, and here also 2 can be taken outside. So that I have written here, sigma an x raised to n equal to 1 to infinity, 3 outside, sigma an minus 1 x raised to n equal to 1 to infinity, plus 2 times sigma x raised to n equal to 1 to infinity. Now in the next step, our goal is to convert all these summations in terms of sum generating function, and remember the formula for generating function is an x raised to n equal to 0 to infinity. So we have to take care that all the summations can be converted in this type of summation, that is sigma an x raised to n equal to 0 to infinity. So here I have sigma an x raised to n, but this is starting from n equal to 1. Similarly here I have x raised to n, but this is not an, it is an minus 1. So I have to rewrite all these things in such a way that I will obtain sigma an x raised to n in the formula and or in the equation, and then that can be replaced by generating function g of x. So for the first summation, this is sigma an x raised to n, but n is starting from 1 to infinity. So if you observe, I can rewrite this sigma an x raised to n equal to 0 to infinity. This I can rewrite as the term corresponding to n equal to 0 is a0 into x raised to 0. X raised to 0 is 1, and plus I can rewrite in this way, sigma an x raised to n equal to 1 to infinity. That means this sigma an x raised to n equal to 1 to infinity equal to this summation minus a0. So I will replace this sigma an x raised to n from n equal to 1 to infinity by sigma an x raised to n minus a0. Now before converting this in terms of this sigma, I have to change the index here. Here I have n minus 1 and I require an. So I am changing the variable of this summation. I will assume that suppose n minus 1 equal to say m. So this n minus 1 will be replaced by m and n will be replaced by m plus 1. And here n starts from 1 to infinity. So if I take n equal to 1, I will obtain m equal to 0. For n equal to 2, I will obtain m equal to 1. That means m will start from 0. So I will have sigma m equal to 0 to infinity a m x raised to n, that is m plus 1. So that I will replace in terms of small m, and this I can again rewrite as sigma x raised to n equal to 0 to infinity minus x raised to 0, that is 1, because this is starting from n equal to 1 to infinity and here this is starting from 0 to infinity. So if I subtract first term corresponding to n equal to 0, I will obtain this summation. In the next step, I have done these things here. This is sigma an x raised to n equal to 0 to infinity minus a0. This summation is replaced by this summation minus a0 equal to 3 times n minus 1 is replaced by m, n is replaced by m plus 1, and n minus 1 equal to m, and n starts from 1, therefore m starts from 0, plus 2 times sigma x raised to n equal to 0 to infinity minus, we have to subtract the term corresponding to n equal to 0, which is x raised to 0, and x raised to 0 is 1. Now this quantity is nothing but generating function g of x, so that we will replace by g of x, and here this x raised to m plus 1 can be written as x raised to m into x, and x is independent of m, therefore we can take x outside summation. So this will be replaced by 3x times sigma am x raised to m. And if you recall, this is nothing but Maclaurin series of 1 over 1 minus x. So that will be replaced by 1 over 1 minus x. And whatever analysis you are doing, you have to mention the reason in the bracket. So this is replaced by gx minus a0, that I have written here. Here x is taken outside the summation and we are left with sigma am x raised to m. This is replaced by 1 over 1 minus x and minus 1. And I have written here, because 1 over 1 minus x is sigma x raised to n equal to 0 to infinity. And we know that this is valid if mod x is less than 1. So here there is an assumption that all the series in these equations are convergent for some values of x, and we are fixing our domain to those values of x only. So that is the assumption that all these sigma or all these infinite series are convergent in some interval. So this is valid if mod x is less than 1. And now if you observe, this is nothing but g of x. This m is dummy index. So if I am writing sigma an x raised to n equal to 0 to infinity, or sigma am x raised to m equal to 0 to infinity, both are the same thing. Therefore this will be replaced by gx in the next step. And value of a0 is 1, that I have substituted here. So I have gx minus 1, 3x times gx plus I multiply this bracket by 2 and I have 2 over 1 minus x minus 2, and I have written that I am using initial condition a0 equal to 1. Now we are interested in the formula of generating function gx in terms of x. So in the next step we will transfer this on left hand side and 1 will be transferred on right hand side, and we have gx minus 3x gx equal to 1 plus 2 over 1 minus x minus 2, and this is 1 minus 2 minus 1 plus 2 over 1 minus x. Here we take gx common and we are left with 1 minus 3x, and in the next step we divide these two terms by 1 minus 3x and we have this form of generating function gx, 2 over 1 minus x into 1 minus 3x minus 1 over 1 minus 3x. Now in the next step I have to rewrite this function of x using partial fractions. So you can see, or if you observe, then this is a proper rational function. Degree of numerator is 0 and degree of denominator is 2. Therefore this is a proper rational function, and if you recall, every proper rational function can be written as sum of partial fractions. So in the next step we have to rewrite this function as a sum of partial fractions, and we assume that this is equal to some constant divided by 1 minus x plus some constant divided by 1 minus 3x, and we have to decide what is capital A and capital B and keep this as it is for the time being. In the next step I have done this work. I have assumed that this is equal to A over 1 minus x plus B over 1 minus 3x. In the next step I multiply this whole equation by 1 minus x into 1 minus 3x. This is multiplied by this quantity, and I have 2 equal to A into 1 minus 3x plus B into 1 minus x. Now these two are linear factors, so I equate them to 0, and whatever value of x I obtain, that I substitute in this number 2, and I am able to decide these coefficients or constants A and B. Similarly, if I equate this to 0, I will have x equal to 1 by 3. So I will put x equal to 1 and x equal to 1 by 3 to decide the constants A and B. First I have taken x equal to 1 in this equation 2, and I have 2 equal to, this is going to be 0 for x equal to 1. If I take x equal to 1 here, I will have A into 1 minus 3, that is minus 2, and therefore A is minus 1. Then I have taken x equal to 1 by 3 in this number 2, and for x equal to 1 by 3 this is going to be 0, and we are left with 2 equal to b times 1 minus 1 by 3, and this is 2 by 3, that is equal to 2b divided by 3. These two will get cancelled and we have b equal to 3. That we substitute here, and we are able to write this function as a sum of two partial fractions. And now we substitute this equation number 3 or value of this rational function in that function formula of gx. So this will be replaced by this minus 1 over 1 minus x plus 3 over 1 minus x. So that I have written here, and we have this quantity minus 1 over 1 minus 3x, that also I have written. Now if you can see, in these two terms we can take 1 over 1 minus 3x, and we have 3 minus 1, that is 2. So finally we have 2 over 1 minus 3x minus 1 over 1 minus x. Now once we are able to write our generating function in this form, we have to decide that for which value of this x, for which value of an we can express this function in terms of this series. We have to decide that what is the formula for an such that I can write 2 over 1 minus 3x in this form. So if you recall, we have seen that if I have this formula for generating function c over 1 minus bx, then formula for an is c into b raised to n, and here c is 2, b is 3, so we have an equal to 2 into 3 raised to n. So that I have written here 2 into 3 raised to n x raised to n. And if I have 1 over 1 minus x, then this is very famous formula. Here constant is 1, so an is 1 into x raised to n. And if you don't want to remember that generating function and corresponding sequence, then also fine. Here you can take 2 outside and you can use this formula. We know that 1 over 1 minus x is sigma x raised to n equal to 0 to infinity. Now instead of x I have 3x, so I will put 3x here, and then I can rewrite this as 3 raised to n into x raised to n and this 2. And here I have an equal to 1. Now in the next step we have taken this x raised to n common. We can combine these two summations because range is from n equal to 0 to infinity. So we have 2 into 3 raised to n into x raised to n minus 1 into x raised to n. So finally I have written this series in this form, an into x raised to n, so that I can compare with this and I can obtain the formula for an. So we have an equal to 2 times 3 raised to n minus 1, n takes the values 0, 1, 2 and so on. This is the required solution, and you can cross verify. You can use your initial condition to check your solution. Here initial condition was a0 equal to 1, so we can verify that whether we obtain a0 equal to 1 or not. So I take n equal to 0 here, and I have a0 equal to 2 times 3 raised to 0 minus 1, and 3 raised to 0 is 1, and I have 2 minus 1, that is 1. So a0 is 1, and that is correct. It is given that value of a0 is 1. That means our solution is correct. So in this way generating functions are also helpful to solve the recurrence relation. And in your question, if they specify that solve the recurrence relation using the method of generating function, then you have to use this method only. If nothing is specified, then you can use method of undetermined coefficients. That will be easy as compared to this method. But if they specify the method, then you must use the method which is specified. Now in this lecture we have discussed how to solve the recurrence relation using generating function, and for that you must be familiar with the formula of generating function. It is gx equal to an x raised to n equal to 0 to infinity, and remember the generating function and corresponding nth term of this sigma. For example, if we have 1 over 1 minus x, then an is 1, and if we have c over 1 minus x, an is c. If I have c over 1 minus bx, then formula for an is c into b raised to n. Similarly, if I have x over 1 minus x whole square, then I will have n times x raised to n, or let me check whether I have written correctly or not. So that all these things we have discussed in earlier lecture number 3. So here if I have x over 1 minus x square, then an equal to n. So that is correct formula. And if you can remember this, your work will be less. And if you are not able to remember, you can use that standard Maclaurin series expansions to write down the corresponding sequence for generating function. And the method is easy. What we have to do is, first you decide what is the degree of given recurrence relation, that is first step. So that will give you the range of n. If your degree of recurrence relation is 1, then n can take the value from 1 to infinity. If degree is 2, then n is from 2 to infinity. In the next step, multiply given recurrence relation by x to the power n, and then take sigma for each term in the recurrence relation, and the range of sigma is nothing but n equal to degree of recurrence relation to infinity. Therefore, you must be able to decide the degree of recurrence relation. Now, once you write down all those terms in terms of sigma notation, or after applying sigma notation, you have to convert all those summations in this form: an into x raised to n equal to 0 to infinity. So once you convert your summations in this form, you can replace this quantity by generating function, that is g of x. And once you can do this, you have to find out the formula for generating function, and then use this type of things, or decide that if you have this formula or this function of x, corresponding sequence is c or constant. If you have this type of function in the generating function, then an is c times b raised to n, and so on. And after that, you will get this type of expression: sigma n equal to 0 to infinity something into x raised to n, and we know that this is sigma an into x raised to n equal to 0 to infinity. So once we convert our right hand side in this form, we can easily compare these two summations, and we are able to decide value of an. And whenever you are doing all these things, that you are writing all those summations in this form, you have to use initial conditions also. If your recurrence relation is of first degree, you will be given one initial condition. If it is of second degree, you will be given two initial conditions. So you have to use those initial conditions once you convert your summations in this form of gx. So this is all about this session. I hope you like it. Thanks for